So let's start. You are welcome once again. Today we are looking at correlation. And if you remember, when I was talking about the different type of tests, I made mention of when you are having association between two quantitative variables. So that is correlation. You remember for chi-square is association between two categorical variables. And for t-test and ANOVA, it's association between categorical exposure and quantitative outcome. So when I say chi-square, association between two categorical variables, it means both the exposure and outcome are categorical. But for the mean and ANOVA, the exposure is categorical. It's the outcome that is quantitative. But in a situation where you can actually look at association between two variables, though in correlation, they don't mention or dependent or independent, but there are the two variables you are looking at association about between them, they are actually in quantitative form. So correlation has to do with number. So let's go into it. In everyday life, to denote some form of association, that is correlation. In statistics terms, we use correlation to denote association between two quantitative variables. We also assume that the association is linear, as on the variable, that is, as the variable increases or decreases a fixed amount for a unit increase or decrease in the other. That is, when you say linear, that is, if this increase if age and weight of a child, both of them are quantitative. So you can quantify age, you can quantify the weight of the child. So if you say as the child increases by 1 month or 2 months, what happened to the weight? As the child is increasing by 1 month, what happened to the weight? So you see that in that situation, you can see, is there any change, whether in opposite direction or in the same direction? Of course, for the sake of age and weight of a child, it has to be in positive in the same direction. As the age increases, the weight is supposed to increase. But there's something, okay, let's say you're able to you quantify the foolishness, childishness of a child. So as the age increases, the childishness will be. So that one is moving in opposite direction. Now, regression, we are talking about correlation, but regression involves estimating the best straight line to maximize association. We just mentioned that one here. But it's by tomorrow, next lecture with positive regression. Correlation describes the strength of association between two variables. Correlation is completely symmetrical. Correlation between A and B is the same thing as correlation between B and A. That's why you're going to get to know that there is no, in correlation, there is no dependent or independent variable. So if the two variables relate to relation, it means that when one changes, the other changes by. So if Y represents dependent variable and X independent variable, this relation is described as regression. So if we are talking about relationship, we talk about regression. But when you talk about just strength of association, we talk about correlation. So a correlation is a measure of how much two random variables vary together, similar to variance. I want to here and I want to understand the origin of correlation. Because if you this Pearson correlation, Pearson, the day I discussed chi-square, I talked about the common chi-square. It's also the first person to describe correlation, Pearson. And that's why you have Pearson chi-square. You also have Pearson correlation coefficient. So let's look at how does it's similar to variance. Variance tell how a single variable vary. Covariance is similar to covariance rather. For variance, tell how a single variable varies. But covariance tell how two variables vary together. For example, now look at covariance. Negative covariance, as one variable increases, the other one decreases, or the opposite direction. One variable decreases, the other one. That is negative. Can you see? One is increasing, the other one is negative. But the one in the middle is near zero covariance, and the one here is positive covariance. As one increases, the other one increases also. Let's use this. This is an illustration of variance and covariance and how it will help you to understand the origin of correlation. Now, you see that we try to see how two variables that quantify vary together. The advert watch, the number of advert watch concerning a product, and the number of packets of the product bought. So we have 5 subjects. Number 1, 2, 3, 4, 5 subjects. So you can see the value of the advert watch, the number of advert, the number of packet bought. The first person watched 5, bought 8. The second person watched 4, bought 9. The third watched 4 and bought 10. The fourth watched 6 and bought 13. And the last one, number 5, watched 8 and bought 15. So you can actually calculate their mean. The mean number of advert watched is 5.4. The mean number of packet bought is 11. And the standard deviation of the advert watch, 1.67. That of packet bought is 2.29. You can actually show this value on a graph, as you see below. If the blue graph is the advert, while the lemon green is packet bought, you see vertically is the number we are talking about, as the number of advert or packet watch, advert watch or packet bought, while horizontal is the person. You see the first one, you see, we have calculated the average. The horizontal line, blue and green line, they are the means. So you know that for some of them, mean is usually in the middle. So if you arrange the value in ascending order, some value will be less than the mean, while some will be higher than mean. You will see for the number of, for the number 1, so if you look at the, though I didn't calculate the difference between, but it's implied. Look at the number 1 person. The number of advert words is 5. And you know that the mean is 5.4. So the mean is just above 0.4, above that value. That's why that value is below the mean. So the distance between that value and the mean is minus 0.4. The same thing, look at the second person, the number of adverts watch, if is 4. And if the mean is 5.4, so that the difference is short by 1 minus 1.4. Because the mean is 5.4, the value of that one is 4. So there's a difference of, so it's less than the mean by minus, at least by 1.4. That's why you put minus here. The third person, the same thing. The fourth person, the value is 6. And that one is above the mean, because the mean is 5.4 and this is 6. So the difference of 0.6 in the positive direction. That's why you are plotting there is now related to the mean. The last person is 8, and then since the mean is 5.4, the difference is 2.8. Okay, now it's plus 2.8 above the mean. So you will see, though you can even see their value against the vertical line, but what that one is just showing is showing the distance. So some are above the mean, some are below the mean. It's the same thing with the number of packet bought. You know the mean is 11, and the first one bought 8, so it's far below 11. That's why, can you see the distance between that one and the mean is -3. The second one bought 9, and the distance between 11 and 9 is -2. That is, 9 is less than 11 by 2. That's why it's minus. Third person is 10, and it's just below by -1. Then the fourth person, 13. So you know the mean now is 11. So that was 2 above the mean. And the last person bought 15, so which is 4 above the mean. So you have what you do now, what you can see on the graph now, that we join the point with the graph, vertical line, showing you the deviation from the mean. You remember, we say deviation from so what you are seeing now is deviation from the mean. Now, what we just want to see is that, do these two variables, the number of advert watch and number of packet ports, co-vary? That's want to look at covariance. Do they vary together? If they actually vary together, as you can see, they actually vary, this one vary together, you will see the graph have the same shape. If you look at the first 3, the number of packets advert watch, the value are below the mean. The same thing with the number of packet board. So both the number of advert watch and packet board, they are below the mean. That's why the graph is in the same direction. While the last two, these values are above the mean. So it shows that these two things, they vary together, they co-vary. But if they don't co-vary, if there's no covariance, or if they can co-vary in opposite, that this is a positive covariance because they are in the same direction. They may co-vary, but not in the same direction. In this situation, for example, as the number of, for the first 3 now, the number of advert watch are below the mean, the number of packet board will be above the mean. Can you see now? So instead of all of them pointing down, that one will be in opposite. Then for these last 2, as the number of advert watch are above the mean, the number of packet will be below the mean. That one will be facing it. It means that they still covary in opposite direction. But if there's no covariance at all, if they don't covary, this graph will be haphazard. One of them, 2 of them may be facing one another, while the other one are apart. No, you won't see any pattern. It means there's no covariance. That's just a pictorial way of explaining covariance. But we can give it quantification. Like for this one now, how do you give it quantification? How do you quantify? How do you calculate variance and covariance? For this same data, you remember our variance is mean square deviation from the mean. That is, if you say x minus s bar square sigma, addition of all of them divided by the degree of freedom, which is n minus 1. So that is variance. So, let's assume that the number of packet advert watch is x, and the number of packet bought is y. So that first one now, we can do, okay, what is the variance for, even though I didn't calculate it, but that's just the formula. But so you see now, that's how we're going to calculate the variance. When we say sigma x minus s bar square, so you can split this into 2 and say sigma x minus s bar then into x minus s bar, because it's x minus s bar square. And that's why we write it 2 times here, over n minus 1. The same thing, the y, maybe the number of packet bought, which is the y, the other one. So, the variance will be sigma y minus y square over n minus 1. So you can split it and say sigma y minus y bar into y minus y bar over n. These are the variances for each of these things. One is to use y to denote one, we use x. So the covariance would be, just if both of them covary, it will just be one of them. Sigma n minus s bar So y minus y by over n minus 1. That is covariance. So if you do that for this data now, the covariance will be 4.25. If you calculate it for this, you slot in a 4.25. Now, one of the problem we now have with covariance, why is intelligent? Because that's what led to correlation. The problem you have with covariance is that large covariance can mean a strong relationship between variables. However, you can't compare variances over data set with different scale. Can you see now, like weight and height? So you cannot use it because it's not standardized. The scale for measurement is different. Weight you'll be talking of the height. If it is measured in meter, which is the SI unit, and you'll be talking 1.3, 1.75, 1.62, all those. If you even go and measure it in a centimeter, you're talking 182. So they are not the same scale. The same thing, you talk about all the other things, blood sugar. Everything has its own scale. So that's why covariance is very difficult to use. So a weak covariance in one data set may be a strong one in a different data set with different scale. Can you see? So it will give you those that have big stick scale. For example, you want to measure kilometer. Somebody a car travel 130, 70 kilometers. Those ones give you big values because that is the nature of the figure. So now, the larger the x and y value, the larger that's what I just said. Similarly, the large unit of measurement for the larger the unit of measurement of x and y, the larger the covariance. I said it. Now, how do you fix the problem? That was what Pearson did. So that's okay. The problem can be fixed by dividing the covariance by the standard deviation of x and y and get the correlation coefficient. So what the intelligent man did was to do this. Let's correlation covariance divided by standard deviation. So remember, if you put covariance, if you remember, the covariance is sigma x minus x bar, y minus y bar over n minus 1. If you divide by the standard deviation of each of them, both x minus x bar over n y times square root. In standard deviation, you have to put the square root there. Square root. Standard deviation is square root of variance. When you divide it, you just do some mathematics there. It will give you what you have. Sigma x minus x bar into y minus y bar over square root of x minus x bar square and square root of y minus y bar square. This is the formula for correlation, Pearson correlation. Or it can be written in this other form. You don't need to cover a crime. Nobody will ask you. It's just the logic behind it. So know that correlation does not have unit. The reason, if you look at it now, when you divide two things of the same unit, the unit cancel out. It's dimensionless. It's just like when we did standard normal distribution. We divide the variance deviation from the mean by the standard deviation. In that situation, the unit of the deviation from the mean, if we are measuring weight, is kilogram. The mean unit of standard deviation is kilogram. Kilogram by kilogram cancel. That's why the z-score is dimensional. It's the same thing here. If maybe you are dealing with height and weight, the unit is both kg and meter or centimeters, this may be. Since you have already divided by their standard deviation, which is the same unit, so it has cancelled out. So what you have is dimensional. It has no unit. So it's standard. So it's the same. So it's universal, like the standard normal curve, z-score. And it's universal. You use in Greek, in engineering, in medicine, in health, anywhere, because it's a standardized measure. So correlation isn't affected by changing in the center, mean, or scale, or variable. So it's not affected by change in the mean. It's not affected by change it's not affected by the unit of measurement. So let's now come back. So what I just did here is to just tell you the mathematical how the intelligent man discover or maybe discover, yes, correlation. Now let's talk more about the meaning of correlation. It's the degree of linear association between two variables. The strength of the association is summarized by this correlation coefficient. So the correlation coefficient is a dimensionless quantity. I've said it's dimensionless, ranging from -1 to +1. So to me, I would like to say that it ranges from 0 to 1, but it can be negative or positive. So it can be from -1 to 0 or from 0 to +1. Anyway, it's between. Because why I say that is that for a particular scenario, if you calculate the correlation, the value can be, it's going to be from, if it's going to be a positive correlation, from 0 to 1, positive. If it's going to be a negative correlation, it's from 0 to negative. But that's what, just take it, it's from, the value cannot be less than -1, cannot be greater than. So a positive correlation is the one in which both variables increase and decrease together, while a negative correlation is the one in which both variables increase. As one variable increases, the other one decreases. If you remember your physics and chemistry, Charles law, you know that Charles' law talk about the temperature, the pressure of a gas is directly proportional to the temperature. As you heat the gas, you heat it, the pressure build up. As you increase the temperature, the pressure go up. So for every unit increase in temperature, the pressure will go up. So that's what we call, if you begin to reduce the temperature, the pressure will begin to come down also. So both the temperature move in the same direction. That is direct. That's what they call it. Remember, mathematics or direct proportion. As one increase, the other one increase. So that is what we call positive correlation here. So what they've called direct proportion in mathematics, we call it positive correlation. And if you remember, if the Boyle's law, it talks about volume and pressure. As the pressure increases, volume decreases. As the pressure decreases, volume increases. So volume and pressure, they move in opposite direction. In that situation, it's inverse proportion. It's inverse, and that is the negative correlation. The inverse proportion is negative correlation in statistics. So when variables are exactly linearly related, the correlation coefficient equal either +1 or -1. So the plus or minus now have to do with the direction, whether it's a positive correlation or negative correlation. I think if it's both of them, it's a direct proportion or inverse proportion. So, but here now we are now talking of what is the strength of association. So if something is perfectly related, what it means that if one A changes by 2, the other one change by 1 or 2, if it's consistent for every 2 change in this one change by a fixed amount, that is all the time. That is correlation is perfect. Now know that correlation is the same thing if it is negative, if one increase by a fixed amount and the other one decrease by that another fixed amount all the time. That is perfect correlation in the negative direction. Know that the correlation coefficient is unaffected by the unit of measurement. I've already said that. The square of the correlation coefficient gives the proportion of the variation of one. To leave this one. This one we talk about. That's what we call it. Talk about it. So let's throw more meaning so that you can perceive it pictorially. Look at the you can see the different type of this correlation, ranging from the positive to negative. That is a sign, but also the strength of the correlation. Look at this one now, the positive, one perfect positive, which is 1. You see, all of them, at one, you know, you plot the other one on x-axis. It doesn't really matter which one plots, because there's nothing like dependent or independent. Any of them can weight and height, any of them can be on y-axis, any of them can be on x-axis. They just know that there's one on y-axis, on x-axis. So as one increased by this also increase. So in that situation, this value will be on a straight line like this. But because it's in positive direction, both of them increase together. Look at the other one that is not perfect, but it's 0.9. It's a little bit scattered, but you can see the direction is moving. The same thing with this one, 0.5. Can you see the direction is moving? So look at this other one, 0.5, moving in opposite direction. That is the negative correlation now. The slope is slide down from left to right. While in positive is from, sorry, it's from, yes. So while in a positive is from slide up from left to right, where the other one slide down. So you can see now the other one is the mirror image. So we still have, though there are some, we'll talk about the value where we quantify when you interpret correlation. Later you get to know that when you do correlation, some people make mistake. They go and use p-value to interpret. P-value cannot interpret correlation because is anyway, I'll talk about it later. Why we don't use p-value to interpret correlation. So correlation coefficient of 0 means there is no linear relationship between x and y. However, other functional relationship may exist. One point to know that if there is no relationship at all between x and y, and how we remain, will certainly be 0, but not vice versa. Perfect one. This one. Let's talk about what we just talked about. We talk about the strength of association. Just give me 1 minute. Let me 1 minute. Okay. I'm back. Sorry. So let's now look at different correlation coefficient. So that thing we just calculated, and there is different way of calculating them because we have for different scenario there are different correlation coefficient. The one that Pearson invented, he was the first to describe it. What is actually calculated is what we call Pearson correlation or product moment correlation coefficient. Now, we usually denote that one by R. So it's parametric in the sense that it's for when you are having two variables that are numeric that follow normal distribution. So we require interval or ratio data for both variables. Then we have one Spearman correlation coefficient, represented as rho. This one is non-parametric. Require ordinal data for both variables. What we mean by ordinal data? You remember ordinal scale, when something you have like education, no formal education, primary, secondary, tertiary. Originally, they are not number, but just rank. So when you rank them, give them number 1, 2, 3, 4. That's ordinal. So in that situation, and whenever you have at least one of those variables you want to correlate, is ordinal. So you cannot use Pearson. You use Spearman. Kendo also is like Pearson. It's like Spearman. But it's better for smaller sample size with large number of tie rank. What do I mean by tie rank? Imagine if you rank maybe your question about this like scale, strongly agree, neutral, disagree, strongly disagree. And many of them, most of the time, agree, too many agree. So in that situation, we have too many tie rank. So Kendo is in that situation better than Spearman. Okay, now let's talk about also, we have also what we call point biserial and biserial. Point biserial is it quantifies association between a continuous variable and a discrete dichotomous variable. A continuous variable, for example, now maybe weight is a continuous variable. Then we now have a discrete dichotomous variable. Dichotomous variable means there are two, either yes or no, two possible values. Can you imagine the other one in weight is a continuous scale, but why this one is either yes or no? It's either of the two values, male or female, yes or no, if there or not there, diabetic, not diabetic, hypertensive, not hypertensive. Those are dichotomous. But the meaning of discrete dichotomy is no continuum underlying the two categories, e.g., dead or alive, male or female. That is, when you have two possible values, that is dichotomous. But it's not as if maybe it was figure before, where you just have a cutoff, you're not dividing into yes or no, or dead or alive. That's the meaning of discrete dichotomous variable. So that's why you use point biserial. Then we have biserial, is not point. Biserial now. Quantify association between a continuous variable and a continuous dichotomous variable. When there is underlying a continuum underlying the two categories, e.g., passing or failing exam. If you see somebody either you pass or fail, there's a continuum that is a figure. Is the person score particular figure, has a mark, and then that's okay. Anything above this is pass. Anything below this is fail. Can you see now? Or maybe you blow blood sugar. You now say, okay, anybody that have blood sugar 126 milligrams per day and above is diabetic. The rest is not diabetic. So diabetic, not diabetic is dichotomous, but it's a continuous dichotomous variable in the sense that there was a continuum underlying. There's a continuum. That is it was a quantitative variable before, before you have the cutoff, cut it. I don't know if it's very clear now. So it's very interesting to know that this person, this Spearman, and tell you most of them were genetics. So I think I don't know if I told you when in the first lecture that, okay, I didn't say that. The people that developed statistics over the years were biologists. Biologists then followed by social scientists. So even though statistics is a branch of mathematics, it was not mathematicians that developed statistics. It was these people that needed. It was not natural science like physics and chemistry that developed statistics. The biology, natural science, yes, biology. It's a major player, followed by the social science. And the reason is very simple. Because I made mention of deterministic and probabilistic model. So all these physics, chemistry, they follow what we call deterministic model. If we say Charles law, since the day they did Charles law, it has not changed. Bohr's law, it has not changed because water contains hydrogen and oxygen, it has not changed. The relationship between pressure and volume of gas is the same. So the same thing with temperature and pressure. It has never changed. If you do it in Nigeria, you do it in America, you do it in Canada, it gives you the same thing. So far, it's the same condition. You get it now. So they follow deterministic model. But when it comes to biological variable, you see that about